All right, welcome back, everyone. So we're continuing on with our transistor analysis. And last time we learned how to analyze these circuits. And so we had a list of steps that we follow through in order to determine what mode we are in. And from there, we can go ahead and apply the models in order to figure out exactly how our transistor is behaving. So what I wanted to do now is go over kind of a more real-world example of using a transistor. And for this application, we're going to be using the transistor as a switch. So let's go ahead and say BJT as a switch. And I think this is one of those things that you hear about all the time. Transistor, it acts like a switch. It acts like a switch. Well, as we know, there are three modes that our transistor can operate in. Cutoff, and cutoff, as we saw from the model last time, both the collector to emitter circuit are open, as well as the base to emitter is open as well. So cutoff mode is very similar to the transistor behaving like an open switch. And saturation on the other side, the current is no longer dictated or controlled by the transistor. It was limited by that collector resistor. And so at that point, we have a fixed 0.2 volt drop between the collector to the emitter. And that essentially could be considered a closed switch. Now, we're going to be focusing on these two modes if we're going to treat our bipolar junction transistor as simply a switch. And indeed, BJTs do get used for this application. And if you're in my 262 class, we're actually going to be doing something very similar. Now, the last mode is linear, but we're not going to be necessarily operating the transistor within this region of its linear mode or linear operation for the sake of using it as a switch. So let's go ahead and let's set up a circuit here that uses a transistor as a switch. Okay, now look at how I've set this up here. We have an LED and we have a 330 ohm current limiting resistor through this entire circuit over here with 5 volts applied to it. And Vin over here, let's take this to be a digital input. Now, for a digital input, is it 5 volt logic? Is it 3.3 volt logic? 1.8 volts? We're going to go with 5 volt logic. So when we're talking about 5 volt logic, we're going to go ahead and treat a digital 1 as being 5 volts and a digital 0 as being 0 volts. So either we're at 5 volts or a logic level 1, or consider this high, or consider this to be true. However you want to think about it, as far as the circuit is concerned, what we care about is the voltage that's being applied. And similarly, for a logic level 0 or low or false, we're going to consider that input to be 0 volts. So what we have here is a transistor circuit that has two different inputs. And so we're going to have to solve this twice for both cases. We're going to have to solve it once with 5 volts applied to the input, or we're going to have to solve it with 0 volts applied to the input. So we're going to go ahead and do that and see how this circuit behaves under these two different conditions that it would be expected to run at in a real system. And so you can think of this VIN as coming from a microcontroller, or coming from your FPGA, or coming from an Arduino, or coming from a Raspberry Pi. Okay, Arduino would be a microcontroller, the Atmega 328. But wherever this logic signal is coming from, you would interface to your system by driving the input to this transistor. And I do need to have a value for this. I forgot to put that up there. Let's give it as being 10K. Okay, so let's go ahead, let's analyze this first under the situation where we have 0 volts applied to the input. So our microcontroller is outputting a logic level low. So let's go ahead and let's redraw this as though we have 0 volts or you can also think of this as being directly tied to ground. If we're applying 0 volts, whether our microcontroller is doing it or we just hardwired this to ground, it's the same thing. We have 0 volts applied to the input through a 10K resistor into the base of our transistor that we said should be behaving like an open or closed switch. We'll find out what mode it's in a second. We have 330 ohms and 5 volts, and down here tied directly to ground. So now if we're going to go ahead and step through our DC analysis, our process, what is the first thing that we're going to do? So I'll do some shorthand steps that we have over here. And this, what we learned last time, those steps, I'm going to refer to as the DC analysis. Okay, so the first thing we do is we solve as linear. And find out what IB is equal to. Okay, so if IB ends up being less than or equal to 0, we're definitely in cutoff mode. If, however, IB is greater than 0, then we have to then find VCE. Okay, so it's my shorthand. So the first thing we need to do is solve this as though we're in the linear mode and find what cutoff, find out what IB is equal to. Now in this situation, what is IB equal to? Look at that base emitter circuit over here. We have 0 volts applied through a 10K resistor into the base of the transistor, and 0 volts on the other side of E. Now, in order to get any current to flow, in order for IB to be greater than 0, we need to have a voltage here that's higher than the voltage drop between the base and the emitter. Remember, we have this diode that's been formed between the base and the emitter. So we need to be greater than that forward voltage that's built inside of the transistor in order to get IB to even flow in the first place. So when we have 0 volts here, we don't have a higher voltage than that forward voltage inside of the transistor, and that's apparent by the linear model. If you look at the linear model, we need to exceed this forward voltage drop. Well, we're not. So IB has to be 0. Well, if we're less than or equal to 0, this must be cutoff, right? So if we're in cutoff, replace the linear model with the cutoff mode or cutoff model and solve for what that is. So let me go ahead and redraw this now that we know we're in cutoff mode. We know that IB is equal to 0. What's IC equal to? Notice we have an open circuit here. We have 5 volts on one side, ground on the other side. This is essentially the same LED circuit that we've looked at. So IC is equal to 0, right? We have 0 current flowing through it. So is this LED on or off? It's off, right? So we can say in this case that the BJT is behaving like an open switch. Now, for completeness, I can go ahead and ask, well, what's VCE? What is VCE in this circuit? We have 0 current flowing through this. We have a 330 ohm resistor up here. I didn't write in the value, but that's 330. VCE is going to be what? Don't say 0 volts. It's going to be 5 volts.
5.
Yeah, exactly. Okay, so we have all the parameters that we're interested in finding. We called this our operating point last time. 0 base current, 0 collector current, and a VCE equal to 5 volts. For all practical purposes, this is an open switch. Okay, and the LED resulted in being off. Let's go ahead and let's now solve this for the other case. As I said, we're either going to be outputting from our microcontroller or digital circuit either 0 volts or 5 volts. So we've solved it for the case of 0 volts, but we're going to need to figure out what happens now when we apply 5 volts to that input. So same exact circuit. However, now we're going to be applying 5 volts to that input. So it's like we just switched that pin over to a logic level 1 or high. Okay, so now to do this, we run through the same DC analysis, those same steps from last time that we just did to determine whether to determine that it was in cutoff mode earlier. So it's just like having a new problem. Okay, so what do we do here? We're going to go ahead and pull out the BJT, replace it with the linear model. Let me redraw this down below. I keep doing that. Now with the linear model, the transistor is what limits the current going through that collector to emitter circuit. With the relationship that IC equals beta times IB. With a 330 ohm resistor in series with the LED. Okay, now what's beta going to be? Now, if you don't have a value for beta, if it's ever not stated, pick beta to be 100. General purpose transistors have a DC gain. That value of beta is somewhere in the ballpark of 100, 120, 80. We can just take it to be 100 if you don't have that value available. So let me go ahead and state for this problem that we took beta to be 100. Okay, now we can go ahead and solve for what the current is for that base current. Well, what's the base current going to be equal to in this problem? Well, IB is going to be equal to 5 volts minus 0.7 volts for the voltage drop between the base and the emitter, and all of that divided by the only thing that's limiting the base current entering this transistor, which is this 10K. Okay, so what does that end up being equal to? Well, it's going to be 0.43 milliamps. So we have 0.43 milliamps entering our transistor on the base. Okay, so we ended up getting a non-zero value for the base current. It's greater than 0, hence we are not in cutoff. So now we need to go ahead and solve for one more parameter to determine whether we're in saturation or we're in linear. Now, in order to solve for the voltage between the collector and the emitter, remember the collector's right here, and the emitter's right there. So we're looking for the voltage drop across the collector and emitter of this transistor. Now, in order to do that, we're assuming that the linear mode is what it's operating in, and we're looking over here at IC equals beta times IB. That's going to give us our collector current. So let's solve for our collector current first so that we can use that in order to determine our collector emitter voltage. So what's IC equal to? Well, it's just going to be 100, because that's our value of beta, times the amount of base current that we already solved for, which we found to be 0.43 milliamps. So what do we get? 100 times 0.43. That gives us 430 milliamps. Sorry, 43 milliamps. Okay, now with the collector current, we can write out an equation to tell us the voltage drop between the collector and the emitter. So we can just treat this as one KVL loop over here. Okay, so 5 volts minus the voltage drop across the 330 ohm and minus the voltage drop across our LED. So it's going to be 5 volts minus. Now we'll take the voltage drop across this LED to be 0.7 volts, and we'll use Ohm's law to figure out the voltage drop across the 330 ohms. Now, the only current that's flowing through this series circuit is the current that's been dictated or controlled by the transistor. So VCE is going to be equal to 5 volts minus 0.7 volt drop from our LED and minus the voltage drop across this resistor. Well, we specify the voltage drop across the resistor just using Ohm's law. V equals IR. Well, I is the collector current going through it, 43 milliamps, times the resistance of it, which is 330 ohms. This, therefore, gives us the voltage between the collector and the emitter, which when you solve this ends up being minus 9.89 volts. Okay. There's no way we should have a negative voltage across our transistor. Something must be wrong. What is wrong is our assumption that this transistor is operating within its linear. So if it's not linear and it's definitely not cutoff, it must be saturation. Okay, so we now know that this transistor is behaving in its saturation mode. So at that point, let's go ahead and let's solve it using the saturation model. So I'm going to pull out the linear model, 5 volts through a 10K. 0.7 volt drop from the base to emitter. And if the transistor is behaving like it's in saturation mode, then we have a 0.2 volt drop that's fixed between the collector and the emitter. Five volts applied to a 330 ohm resistor in series with our LED. And now, the base current didn't change. Our original calculation for the base current is still valid, so there's no need to resolve for this. We know that IB is equal to 0.43 milliamps. However, our collector current definitely has changed. And our VCE has changed. So let's go ahead, let's solve for our collector current first. What's our collector current equal to? Well, it's not the same as before, because we were running within its linear region. This was limiting the current to something. Now it is not. It just has a fixed 0.2 volt drop. So I have, if you look again at this KVL loop here, I have 5 volts minus a voltage drop of whatever across this 330 ohm resistor, but across the diode I have a fixed 0.7 volts, and across the transistor between the collector and emitter I have a fixed 0.2 volts. So the only thing in this circuit that's actually limiting the current is this 330 ohms. So all we need to do, if we look at Ohm's law here, is to find out what the voltage drop is across this 330 ohm resistor and divide that voltage by the resistance, and that'll end up giving us our collector current. So we can do 5 volts minus 0.7 volts, so we have a fixed voltage drop across this diode, minus 0.2 volts from the voltage drop across the collector emitter of our transistor. And now we can divide this voltage drop, because this is the voltage drop across the 330 ohms, right? All of these other voltage drops have been accounted for, so I just used KVL to find out the voltage drop across the resistor, divide that by the resistance, and we have the collector current. So what does that end up being? $12.4 milliamps. Okay, and that's kind of a reasonable amount of current for an LED to be driven. Now, what's VCE equal to? Just to finish this off, well, it's equal to 0.2 volts. By definition, because we have a 0.2 volt drop between the collector and emitter. Well, needless to say, 12.4 milliamps flowing through our LED is enough to make it on. And so this is a perfect example of using our LED as, using our transistor as a switch. So in one case we have saturation, and in the other case we had cutoff. Okay, now a couple of things to point out over here. Where is the current coming from that's being used to drive our LED? Our LED is being turned on Because of the collector current. Where's the collector current coming from? Well, it's coming from our 5-volt source. It's not coming from the output of this microcontroller. See what we did there? So we're using the transistor in order to dictate the flow of current through our diode coming from our external power, not being supplied from inside of the device. So if I go ahead and draw this as being connected to an 8051 or any other microcontroller for that matter, and let's go ahead and say the LED is on. And it's on because we are driving this output with a logic level high. Well, what did we find IB was equal to? It was equal to 0.43 milliamps. Right? So for the case of turning this LED on, none of the current that's actually being used to turn on this LED, which we found to be 12.4 milliamps, came from the microcontroller. So we're using this transistor as a driver circuit for turning our LED on and off. So if you're in my 262 class, you know that taking a digital device like this and trying to draw more than 1 milliamp out of it, right? Because look at the current has to come, this 0.43 milliamps has to come from inside of the 8051. Well, we don't like to actually source more current than say about 1 milliamp. Now it depends on the device, it depends on the part, but generally speaking, for these logic pins of a microcontroller or any digital device, you don't want to source more than 1 milliamp. You'll stress out the internal circuitry. You'll heat up the part too much. You'll cause some damage. You may get resets on your device. There's a lot of bad things that happen. And generally speaking, you don't want to sink more than 10 milliamps. You don't want more than 10 milliamps coming into the device. So by using this transistor driver circuit over here, we now have the case of when 5 volts is output that we get our LED being turned on, but it's not being done by the microcontroller. The current is actually being controlled by the transistor. So this is a great usage, great application of using a BJT so that we can safeguard our digital devices from sinking or sourcing too much current. Instead, you put the burden on the circuit over here and on the transistor to actually control that flow of current. Does it make sense? Sweet. Okay. So that's how, that's generally how we do that. And we're using the transistor as just a switch. Let me grab some more paper. Now, there is one thing I haven't showed how to calculate yet, which is the power being dissipated by the transistor. So let's go ahead and let's look at this situation. Now, I won't have to calculate the power being dissipated by the transistor when it's in cutoff, because power is equal to current times voltage, right? Well, if you want to know the power being dissipated by the BJT, let's go ahead, let's do it first over here, and then I'll show you why we don't really have to take that into account for the case of when we're in cutoff. So over here, we have a 0.2 volt drop across the transistor when it is in saturation mode. So we're looking at this in the case of when we have 5 volts applied to the input. Okay, now for calculating the power dissipated by the BJT transistor, I'll just call it PBJT. PBJT, right? The power dissipated by the bipolar junction transistor, or it's peanut butter jelly time. So, how do we go ahead and calculate it? Well, it's going to be current through the transistor, which is IC, times the voltage drop across the transistor, which is VCE. And we know what VCE is. It's going to be 0.2 volts. And we know what IC is. It's 12.4 milliamps. So what do we end up getting for the power dissipated? Well, let's go ahead and calculate that out. Now, 12.4 milliamps is 0.012 amps times 0.2 volts gives us 2.4 milliwatts. So pretty easy to calculate the power being dissipated by the transistor. And if you're using a transistor as a switch, where it's going to be fully on and fully open, not a bad idea to make sure that your transistor is operating at a safe level. Now, it depends on what transistor you're using, how much power you can safely dissipate. That being said, 2.4 milliwatts is very safe for this transistor. Usually you can do up to like 20 milliamps in your general purpose NPN transistors, generally speaking about 20 milliamps max. But 2.4 milliwatts of power dissipation generally is safe. Okay? So that's how we can go ahead and calculate the power. Now, I did say we don't really have to do that for the case of when we're in cutoff. Reason for that is because IC is equal to 0. So if you look at the power dissipation by this, you're going to end up I is equal to 0 amps times, it doesn't matter what the voltage drop is. In this case, it's 5 volts, but we have 0 current flowing through it. So we have 0 power being dissipated by the transistor. Okay? So when you're in cutoff, current's not that big of a deal. But when you're in saturation or linear, definitely you should pay attention to what the power being dissipated is. Okay, any questions on that?
the power dissipated always going to be 0.2 volts? Or just depending on the resistor or transistor?
For a BJT, the VCE term of your power calculation will always be 0.2 volts if you're in saturation. So this we would call the saturation voltage. And that is just a given value. Kind of like how we have a 0.7 volt drop for a silicon based diode. If we're in saturation mode, so if we're in one of our three modes, if we're in saturation, you're going to always get 0.2 volts between the collector and the emitter. But that's only half of the equation for calculating your power. You still need to go ahead and figure out what your collector current is. Because if your collector current is too high, let's just say it was like 40 milliamps, now your transistor is going to get toasty. Does that make sense?
Yeah, thanks.
Cool. Any other questions? Okay, so let me go ahead and pause there, and let's see, we had 26 people in. I'll talk about a couple of things on the side.